So again, thank you everyone for coming out to our VCAP webinar series. Today we're going to be troubleshooting memory performance problems. And again, it's myself, Sean MacArthur, and David Sellens, and there's our corresponding email addresses up there. So here's some of our certifications as we've been over before. Lots of VMware, lots of Microsoft, and some other certifications that we don't have listed up there. As a company, we do a lot of performance analysis on VMware, on Active Directory, Exchange, DR, SQL, all kinds of cool stuff for pretty much big companies all over the world. So today we're going to look at troubleshooting virtual machine memory performance problems. We have a lot of stuff. It may actually go a tad bit over an hour today, a little bit longer than I was hoping for, but we got some pretty good stuff we're going to cover. So look at the basics here when we look at virtual machine memory. We have a host, an ESXi host, which has been assigned or has been built with a certain amount of physical memory. So when you see the terminology physical memory, you're looking at my ESX host is a Dell box and it's got 32 gigs of physical memory or 64 or 128 or whatever you got in it. We then build our virtual machines, and when we build the virtual machines, we give it virtual hardware, like the amount of virtual CPUs we want it to have, the amount of virtual memory we want it to have. So the virtual memory we assign to the VM is what they call the virtual memory. And then we have the guest physical memory there. So the memory visible to the guest OS running within the virtual machine. Now, one of the big things when you talk about virtualization is the ability to run more than one VM on a single host. And that's the reason we virtualize. And the reason we do that is we realize that a domain controller probably doesn't need 8 CPUs and 32 gigs of RAM. And a lot of DCs are built with quad-core proc and 4 to 8 gigs of RAM on a physical machine. We realize they don't even need that much. So by being able to limit these VMs that don't need as much, and then having VMs that are very similar, it allows us to deduplicate the memory and allows us to run a lot more VMs on a single host. Now, the concept of memory deduplication and memory overcommitment is this. I build a VM and give it 10 gigs of RAM. Now, it's only using 1 gig. And I build 10 of these VMs. And I sit there and go, okay, well, 10 VMs, all using a gig, that's 10 gigs of RAM. I could build my host with 16 gigs of RAM and I'm good to go. Well, that's what we call memory overcommitment, because I built those VMs actually with 10 gigs of RAM. So if they all maxed out and started using all 10 gigs of RAM, theoretically, I would need 100 gigs of RAM in my host, and I've only got 16. So that's a problem. Now, what else is interesting is when you run VMs that are very similar, maybe I have a DHCP server running on Windows 2008, and I have a DNS server running on 2008, and I have a file and print server running on 2008. They're all running Windows, very similar code, and what you're going to see is going to happen is the ESXi host is going to analyze all these virtual machines while they're running and say, wow, we have all these memory pages between VM number 1, 2, and 3 that are the same. So instead of storing them uniquely, we're going to store them together and deduplicate them. And because of that, it allows us to get this overcommitment. So what's neat here on this slide is that we had a host with 64 gigs of RAM in it, and we built some VMs running Windows XP, which we all know is outdated, and it had 512 megs of RAM in each VM. Now, just doing basic math, you're sitting there going, okay, well, we would need about 89 gigs of RAM to power that on. A little bit of overhead, we would need about 91 gigs of RAM to get all those powered on. But if you look at this actual host right here, we've got 178 VMs running, and we're using 19 gigs of actual memory because of the memory techniques that VMware has built into their virtual hypervisor, which is awesome. We actually have a series we did comparing Hyper-V to VMware, and we're able to power up just a whole much more VMs on VMware because of the way it utilizes memory, which is just awesome. Now, one of the things you can do to utilize memory is what's called transparent page sharing. Now, there's two types of transparent page sharing. We have inter-VM transparent page sharing, and what we'll talk about on the next slide is intra-VM transparent page sharing. So when we look at inter-VM, what that means is that we've got multiple VMs running on the same host, and memory that's duplicated between one VM and the other is shared. So it's deduplicated onto memory as read-only. And then if one of the VMs needs to make a change to that memory, it does what's called a copy on write, copies it to a new memory space, and makes changes to that memory. Now, if that memory then goes back to where it was the same as the other two VMs in this case, then it can put it back into that shared pool. And that's transparent page sharing, inter-VM. Now with intra-VM, with that, the TPS will deduplicate identical pages of memory within each VM. So my Exchange server, if it's got duplicate pages of memory, it will share those between itself, but it won't do it with another one when we're talking intra-VM. So inter-VM between other VMs, intra within itself only. Now what's interesting is inter and intra were enabled by default from 3.0 all the way through 5.5. Well, VMware came up with a new security model in 6 that said security by default. And even though nobody has ever hacked these shared read-only pages, VMware has made it to where by default 6.0 inter-VM page sharing is disabled. And they came out with patches for 5.0, 5.1, and 5.5. And if you patch your host, it is now disabled by default in those particular OSs as well. So we have a KB article down there at the bottom that demonstrates that, but it is. Now, some other settings we're going to talk about here, and we're going to get into some of the settings, and these are on the advanced settings of your host. But the mem share scan time and the mem share scan gigahertz, this controls the rate that ESX is going to go out and look at VMs and say, what is shared from VM number 1 to 2 to 3? And we can control the rate at how it's doing that. Now, the other thing we're going to look at is what's called the salt time. When we look at the salt value, mem.shareForce salting. This is enabled on the host, and we can control what kind of inter or intra VM setting we want. So if we choose 0, for example, inter VM transparent page sharing is disabled, but intra VM is enabled. And if you look at some of the other values that we have down here, 1, 2, we can set those up. Now, when we look at enabling or disabling TPS salt for a host, it's pretty easy to do. We click on our host, go to the host configuration tab, go to advanced settings. Now, there's advanced settings for hardware and software. We're going to go to the one under software, and then we'll look for memory over there. And you'll see I got memory highlighted there. And the one setting we're going to look there is mem.shareForce salting. And we can set that value to whatever we want it to be, 0 to disable it, 1 or 2 to enable it, and whatever level we want it to be based upon that chart on the previous slide. Now, once we make this change on our host, it goes into effect immediately, but for our virtual machines to actually use it, we have to vMotion the VMs to a different host and then bring them back, or shut down the VM completely, not just a restart, but shut it down and then power it back on to get access to those new settings. I also showed some of the other settings here, the share max rate, the mem share scan gigahertz, and then there's actually below that, there's another one as well that you'll want to set. Now for a VM, we can enable it on a per VM basis as well. Now it's not recommended to disable it on a per VM basis, but you can. Just go to settings of your VM, options, go to your general on the options tab there, go to advanced configuration underneath there, then go to configuration parameters down at the bottom button there, and it'll pull this up here. You'll then create a new line, schedule.mem pshare salt, and then we'll put our string in there that we want for that, whatever value we want there. And we can enable or disable on a per VM basis. Now, when we look at going back to the basics of looking at memory on a VM, you'll see that we have several different things we can look at. The memory size. And with this is how much memory we've assigned to the VM when we built it. So 64 gigs, 16 gigs, 8 gigs, 4, whatever it is. The allocated memory, which is the memory assigned to the applications running inside the virtual machine. The active memory, so the allocated memory, which has been recently accessed or used by applications. Idle memory, allocated memory, not recently accessed or used, and the free memory, which has not been assigned. Now, if we look at this over here, we'll see when we look at the memory of our particular VM, you can see that we have color codes over here. We can see over here consumed memory in this particular case is 4.94 gigs, and overhead is 60 megs. Now, this top part I'm looking at is host memory. Get a pen here. So this part here is host memory. Then down here we have it on the guest. So when we look at this particular guest, you'll see we got the color codes. Real simple here. This VM has 4.86 gigs of private memory, which is the dark green there, about 1.14 gigs of shared memory with other VMs through transparent page sharing. Some good things here. We don't have any swap memory. We don't have any compressed memory. We don't have any balloon memory. That's all good. We don't have any unaccessed memory. So those are all good values that we want to see there. And we've got about 300 megs of active memory. So, all right. That's how we've got this guy here configured. And this guy has 6 gigs of memory. How can I tell that? Well, if I look at my guest memory down here, I can see it's configured for 6 gig right there. So, all right. Well, what causes potential memory problems? Several things. Number one, too much virtual memory in a VM is bad. Too little virtual memory is bad. We want to come up with what I like to call right sizing. We need to not just be like McDonald's and supersize everything, which is honestly what most people do in their VMware environment. They supersize all their VMs and they build them way too big. Now, I'm not saying that you should go to your SQL server that needs 32 gigs of RAM and only give it 1 gig of RAM. Yeah, that would definitely save memory on your host, but your SQL server is going to run like crap. What we need to do is, instead of throwing 32 at that SQL server, we need to figure out exactly how much memory does that SQL server need. Yeah, some guy tells us, some vendor says it's got to have 32 gigs. Okay, great, but what's it using? We need to analyze this VM and figure out it truly needs 8 gigs of RAM. Giving it 1, it's going to run like crap. Giving it 32, it's going to run like crap. You want to give it exactly what it needs, which is 8. So we have to figure out exactly what it needs, and there's some ways to do that. Virtual swap, we'll talk a little bit more about this, but when you build your VM too big, it builds your virtual swap too big. Your ballooning. Ballooning is used when the host is running out of memory. So it's not a bad thing to do ballooning, but if you're ballooning on a regular basis, you got one of two problems. Number one, your host doesn't have enough memory, or number two, your VMs are configured with too much memory. So we'll take a look at that as well. NUMA, again, we'll get into that a little bit more later, but that's where you have the CPUs on your motherboard you want to kind of fit within a simple slot. Now, another thing that's used incorrectly quite a bit is the next two things we got here, resource pool. So when we look at resource pool, a lot of people use resource pools to organize objects, and that's not what they're meant to do. If you want to organize objects, go to the virtual machines and templates view and create folders underneath there and organize the VMs to your heart's content. No big deal. They're also not used to set permissions. Although we can set permissions and we can use resource pools to organize objects, you don't want to do that because resource pools will actually limit the resources available to objects. So you want to be very careful using these, that you're using them correctly. Reservations, limits, and shares. Reservations are just the amount of, in this case, memory that you're going to guarantee that the VM will have. How much physical memory is guaranteed that VM has. limit how much physical memory we're going to limit the VM to using. So I've configured the VM for 8 gigs of RAM. I put a 4 gig limit. It'll still show 8 gigs of RAM for the VM, but it will never get more than 4 gigs of physical memory available to that VM. So where does the other 4 gigs come from? Well, it comes from the swap file. Now, is there any guarantee that I can give it those 4 gigs? No, there's not. You know, maybe I'm only able to give it 2 in that particular case. But if I could give it 20, I'll never give it more than 4. Doesn't matter. Now, just because we've configured our VM correctly, we've given it that 8 gigs of RAM it's supposed to have, well, maybe we're running too many VMs on that host, and maybe our host does not have enough memory for all the VMs that we're running. So limited host or VM resources and too many VMs running on a host are common problems that you might see. When you look at the balloon driver, one of the things you want to do for every VM that's running Windows or Linux is install VMware tools. And that installs drivers for the VMXNet NICs, that installs video drivers, sound drivers, all kinds of stuff. And one of the other drivers it installs is what's called the balloon driver. Now, typically, the balloon driver is not doing anything. It's just sitting there kind of hanging out doing nothing. But when your host starts running out of memory, you have to think, okay, well, why is my host running out of memory? Well, it's running out of memory because we powered on too many VMs. So if it's running out of memory because we powered out on too many VMs, where can the host take memory from? Well, there's only one place, from the VMs. Well, how does that work? Well, when the VM is running out of memory, or the host is running out of memory, it starts blowing up this balloon driver, which is kind of like, it's a process that runs in there. It's called vmemctl, and it starts using memory and using memory, and it will give that back to the host so the host can use it. So let's say the host needs 50 megabytes of memory, and I've got 10 VMs running. Well, it'll go to all 10 VMs and just blow this balloon driver up a little bit to where it's only taking 5 megs per VM. That's not very much. Gives that to the host. Well, now the host needs 100. Okay, well, it bumps that balloon driver up to 10 megs. Gives that back to the host. Well, now the host doesn't need anything, so that balloon driver drops down to nothing and gives that back. Now, when we look at this here, the driver is always loaded, but unless it needs it, it won't use it. So it'll go up and down as needed. And when we go back to the slide here and look at this, you'll see my ballooning was doing 0 ballooning. That's great. We don't want it to be doing any ballooning. Short-term temporary ballooning, not a big deal. That's what it was designed for. Long-term ballooning, we need to either shut off some VMs, adjust the memory in the VMs, or add more memory to the host. Now, the VM kernel swap. Before we get into this, I want to talk about basic computers, because a lot of people have the terminology wrong on VM kernel swap. When I have a physical, let's say, desktop computer sitting here, and my desktop has 4 gigs of memory on there. Now, if I am running, let's say, Windows 7, and I've got like a CAD program on there, and I need more than 4 gigs of memory, where am I going to get it from? Well, the place I'm going to get it from is 4 gigs from my physical memory, and let's say I need 6 gigs total. It's going to take 2 gigs from a file called pagefile.sys. I'm not going to write the whole thing. Well, I guess I will. Pagefile.sys. Okay, so my operating system is going to seem like it has 6 gigs of memory, but it's really only got 4 gigs of physical memory. We're giving it 2 from this pagefile.sys, which of course is a file that runs on an operating system on a disk. So it is, of course, slower than memory. Well, why do I bring that up? The process of moving whatever things like the CAD program over to virtual memory and taking it out of kernel mode memory is called paging. It's important that you understand the difference between paging and swapping. Windows does paging. Now, VMware creates a swap file. Every time you go to create a VM, it creates a swap file. Excuse me, I said every time you create a VM. Every time you power the VM on, it goes to create a swap file. Well, how big is that swap file? Well, it's basically however much memory you give the VM. So if I give the VM 10 gigs of physical memory, it's going to create a 10 gig swap file. So let's look at a couple of things here, then we'll go back to an example. A VM will not power on if it can't create the swap file. Well, why can't it create the swap file? Well, because it doesn't have enough free space to create that 10 gig file. Well, let's think about this. If my VMs only needed 1 gig of memory, and I built them all with 10 gigs of memory, and I have 10 VMs, I would be storing 100 gigs of swap files on some data store somewhere. So I'm using up all of this hard drive space and all of the physical memory on my server because I built my VMs too big. Now, the actual way you calculate it is if your VM has a reservation set on it, which means I'm guaranteeing a certain amount of memory for this VM, then you would take however much you've configured the VM for, 10 gigs of memory minus whatever that reservation is. Let's say it's a 2 gig reservation. So you would have an 8 gig swap file in that case because you're guaranteed to have 2 gigs of physical memory at all times. In fact, if I can't get that guaranteed 2 gigs of physical memory, it won't even let me power the VM on. Now, this next bullet point, the VM kernel can swap the entire amount of unreserved memory if the host memory is needed. Okay, let's go back to my drawing I had here of my little Dell computer, and we've got the 4 gig physical box down here, and we're paging 2 gigs of page file. So I virtualize this guy, and we make it a VM. So this is now a VM, not a physical box. Now, ultimately, this VM is using 6 gigs of memory. That's why we're paging all the time. So I should give this VM 6, potentially 8 gigs of memory, but I don't. I only give it 4. Now, all things being perfect, that 4 gigs of RAM should run from physical memory. But things aren't always perfect. What happens if I can only give this VM 2 gigs of physical memory? Well, now it gets really interesting. The VM thinks it has 4 gigs of memory. So I'm giving it 2 gigs of physical, but where's the other 2 gigs coming from? The other 2 gigs is coming from the swap file. So in this particular case, we got 2 physical, we've got 2 from the swap file, and we've got 2 that are running from the page file. And of course, the swap and the page file are all running on disk, and we've got 2 running on actual physical. So this VM is running terrible. So it's not running good at all, which is not what you want. Ultimately, we want to be able to look at this VM, we want to be able to give it 4, look at how much it's paging, and ultimately bump it to 6. But if you don't have the memory resources, you don't have them. Well, when do we do this swapping? Well, the first thing we do is we do ballooning, and if maybe we max that balloon out, maybe we didn't install VMware tools, so ballooning is not even an option. Maybe the balloon driver just can't borrow memory fast enough, so it's got to go swapping, or maybe someone explicitly disabled it, which doesn't typically happen. And then it would use this swap file. Now, with ESX 5.0, the thing that you can do is what Richard asked about. Should you build your VM with multiple sockets or multiple cores per socket? And depending on how your physical computer is laid out, let's say I have a 2-socket, 6-core per socket box for a total of 12 cores, hyper-threaded to 24. Well, on that physical box, if we're running an operating system on there, then each NUMA node consists of 1 socket with 6 cores. Now, we've also put memory in that computer. Let's say we've got 64 gigs of memory in that computer. Well, 32 gigs of memory is going to be on 1 NUMA node along with 1 socket, and 32 gigs of memory will be on the other NUMA node and that other socket. In that particular case, you would never want to build a VM bigger than 6 cores and bigger than 32 gigs of memory. Could I do it? Sure. I could do it all day long. I could build my VM and give it 40 gigs, 60 gigs. Heck, I could give it 100 gigs of memory if I wanted to. The problem is if I build it with more than 32 gigs of memory, the only way it's going to access more than 32 gigs of memory is it's going to cross that memory bus and have to go between the NUMA nodes. So you want to try and make your VMs no bigger than whatever size your NUMA node is on the physical server. So although it is possible to make it bigger, you don't want to necessarily. Now, I'm going to let Dave talk about the next few slides and then go into some demos of some of these things using esxtop. So Dave, you want to talk about the next few slides?
Okay. VMware has, how do I want to put this? Well, let's just hit this slide here. If in a normal situation, our consumed host memory, this is the amount of memory that the VM has, physical memory that the VM has assigned to it. And I'm talking about real physical memory on the host that's assigned to it, is consumed host memory. And in most cases, that's going to be greater than the active. This is our goal, to make sure that, of course, as the VM is touching memory, that memory is actually loaded in the physical RAM. It is possible to see that the consumed might be less than the active guest. Now, two things could cause this. We may not have enough physical memory on the host, so the host hasn't been able to give it to the guest, or transparent page sharing actually reduces the consumed host memory, so that and that is generally just fine. So this is an indication, though, that there may be a problem. We need to then go look at the transparent page sharing, the shared memory, and see if maybe that is satisfying it, or if we've got balloon or swap or compression going on that is reclaiming some memory and causing some performance drops. So now, go ahead and go to the next slide. I don't have control of the slide deck. I was clicking on it like crazy. Now, as Sean said a moment ago, VMware is trying to maintain, in general terms, a 6% of buffer of free memory, and when it starts eating into that free memory, it starts going through the reclamation process. In general terms, at 6% it starts ballooning, at 4% it starts compressing, and at 2% it starts swapping in order to maintain its buffer. Now, that's not actually accurate. In general, you could talk about it that way, but really what's happening is it calculates a number that they call the min-free percent, okay? And it would not make sense on a host with 512 gig of memory to keep 6% of that unused. That just is kind of ludicrous. So instead, it calculates a min-free percent value, and it starts ballooning actually at 64% of that value, compressing at 32 and swapping at 16%. So it's kind of like taxes, and it's decremented. Go ahead and go to the next slide. And so out of the first 4 gig, it is truly 6%. Out of the next 8, it's 4%. Out of the next 16, it's 2. And then any memory over 29 gig on the physical host, it's only maintaining 1%. So we actually have some hosts that are running 512 gig of RAM in our data center, and that ends up being somewhere around, when you calculate it out, between 1.5% and 2% is all it's really maintaining. To give an example, let's go ahead and go to the next slide where we got more detail on the example. Out of the first, here's an example. We got 96 gig of memory, and we're taking 6% of the first 4 gig. That's 245. 4% of the next 8 is 327. 2% of the next 16 is another 327. And 1% of everything over 29 gig gives us another not quite 700 megabytes. So our min-free percent is 1.6 gig, 1,597 meg. So at 1,597, what's happening at that point is that it's breaking up any large pages, and it's aggressively using transparent page sharing. Normally, transparent page sharing runs in the background at a very low priority, and you can set, what what CPU and cycle and so forth that it's running at. But when it hits that min-free percent, it starts aggressively transparent page sharing. It raises the priority of that job. At 64% of that 1.6 gig, or around 1.244, it starts ballooning, and at 500 it starts compressing, and at 255 you see here it's actually using the kernel swap. Okay, so trying to keep some kind of buffer. All right, let's see, what's the next slide there, Sean? So a lot of metrics we're going to be looking at, and in both our GUI and in our graphical user interface, or Windows client, or the web client either, we can look at the amount of swap or the swap in or swap out rates. So if we see swap, our next step is to go in and look at the rate and see, is it currently swapping in and out or not. Swap megabytes is the total amount. Swap reads, swap writes, as you see within the esxtop, or swap current and swap target. Current is what's currently swapped, obviously. Target is what it's asking for, so what it's moving toward. And then wait time due to swap, percent swap wait time, that's actually under the CPU counters. Okay, and of course on the balloon side we can see balloon. We've also got balloon in and balloon out type counters as well, mem control megabytes, and again there's a target on balloon as well, as it's requesting memory from the VMs. What is it targeting, asking for from those virtual machines? So why don't you go ahead and make me presenter, and let's look at some interesting examples here.
All right, you got it.
And what I'm looking at here is an ESX host 136, and let's go see what we've got here. I've got the host, I've got a couple of VMs running here. Notice the warnings on them. Those warnings are indeed memory alarms. What these two VMs are doing is they're running a memory test. So they're just churning through the memory, cycling through it over and over and over again, reading, writing, and so forth as they're doing that. These VMs are each 3 gig of RAM, and the host has 10 gig, okay? So it's got 10 gigs. So I've got 6 gig of virtual machines running. You can see my memory usage at the moment is about 3 as it's cycling through. Now that varies as we go through here. So here's a graph, as I've been looking at this since about the time I started this guy up here, right before we started the webinar. And granted is 6 gig. I've granted to the VM 6 gig. Consumed, however, is a bit less than that, because I actually have some very nice transparent page sharing going on. In fact, it's been going up and down here, the transparent page sharing, as it goes through different tests and writes and then reads, and maybe it writes some different value. It may be writing rolling zeros or writing some other value to memory. So right now I'm seeing 3 gig, but the shared common's only 12K. So I've written all the memory with the same value, and the actual space of physical RAM is 12K, but the amount of memory addressed within that shared common block is 3 gigabytes. And you can see here at different times it's reached up to 5 gig and never had more than 12K in it. So very, very efficient transparent page sharing, and indeed this is within these VMs occurring here, not multiple VMs going to the same. Since I've got 2 VMs, I suppose that'd be about 6K if it were doing inter VM transparent page sharing. So this, let me get a different window up here. I've actually got this guy blown up into a full page chart here. So So here's my active. Indeed, six gig is active. It's actually hitting that memory. Consumes 3. Shared is 3. There's my 6 gig. Part of it's in consumed, part of it's in shared. Granted, it's been up to 6. It's going up and down a little bit as it's moving some of that memory, oddly enough, in and out of swap. Even though I'm not at that 6% barrier, what we're seeing here in version 6 is that they're being even more aggressive about using the kernel swap. And here you see that my swap has been going up and down as the different types of tests occur here. So I really need to look a little deeper and see, okay, what's going on? How heavily is it swapping? And indeed, you see here, and my chart's kind of wavering down here at the bottom. I can't really see it, but you can see that I'm doing anywhere from 4 meg to 6 meg, occasionally 0 bytes per second of swap in, and had a couple of really nasty spikes as it was swapping out memory here, adding to that kernel swap. So that 6% business is not happening here within this environment, partially because guess what? No balloon driver. The particularly memory test we're using here has no balloon driver at all, so this is causing things to be a bit more aggressive here. I'm actually seeing some compression going on. At the moment it's down near 0, but it has been using some compression. It seems to be coming down for the most part. But again, we can look at the compression rate. We see at one point it jumped. In fact, as this peak right here hit, that was when our compressed went up again. Okay, so we can see the compression rate. Balloon, never ballooned because we don't have the balloon driver in here. So you can see here that VMware in version 6 has gotten more aggressive than just that 6%, 4%, 2% business that we were just talking about. Now let's have a little bit more fun. I'm going to crank up another 1 or 2 of these guys and see what happens. Power on this one, and let's go open a console to it and get that mem test cranked up. We'll really force this guy to hit that even higher, and we'll run this mem test. That gets us up to 9 gig on our 10 gig machine, and then we'll do one more, which will actually overcommit it and watch it go. This is a little boot CD that has, as you can see, a number of different tests in it, multiple memory tests, in fact. So as we watch this a little longer, now we're overcommitted. We're running 12 gig on a 10 gig system. And let's go back to the full page graph. A little easier to see. Active is up to the full 10 gig. Can't have really more than 10 gig active without some really hefty paging and swapping, because we've only got 10 gig of physical memory. Granted is climbing. My swap is also climbing. That's not a big surprise. Compression rates is going up as we're compressing memory. It's trying to compress even more aggressively than swapping, but the swap is going to come up. So as it goes through the first couple of cycles of that mem test, we're loading up more and more, and we're going to be forcing more and more into the kernel swap, more and more into the compressed. Here's our compressed is now, just up to a gig is all. The memory isn't apparently very compressible. It's using transparent page sharing as much as possible. So it, remember, that's running at low priority in the background for the most part. and continuing to climb as we address more and more of that memory. Boom, kaboom, kaboom. While we're waiting on that to settle a little bit, oops, that's not the one I wanted to go to. I wanted to come in here. This is our production system. This is one of our big hosts. And we'll see in here that we're not going to see any compression or any of that here on this guy. The default, no balloon. We've got consumed of 200 gig. Granted, 200, there's some overhead in there that's showing up under the consumed. Shared common is about a gig here. Shared is not displayed by default. If I want to see shared, I need to come in and pick it. If I want to see compressed, I have to pick it too. It's generally down near the bottom. And do have a little compressed. This probably occurred some long ago when it might have been under a little bit of pressure. And here's my shared and shared common. The difference between shared and shared common is how much is being saved due to transparent page sharing. Now, since they've disabled inter-VM page sharing, I'm not saving a whole lot due to transparent page sharing. If I were to go back and re-enable inter-VM, then I would see a lot more transparent page sharing on here. In fact, I've seen it as high as a savings of 40 or 50 gig here, 10 to 15% of the host memory due to transparent page sharing before they disabled it in here. This is, of course, just within each VM, it's able to share and save about, 3.4 gig is all with memory that's identical within each of the VMs. Okay. And if I pick one of the others just for grins.
So Dave, is it a good idea or a best practice to, even though it's been disabled by default with 6, is it best practice to re-enable that page sharing, inter-VM page sharing?
Well, that's a good question. It's according to how sensitive you are to security issues.
And
nobody has really seen a security or a hack that's been able to take advantage of transparent page sharing. So if you've got a lot of VMs that are the same, particularly in a desktop environment, VMware View actually offers an ability to deal with that salting values and turn it on just for the View desktops where you're running a whole bunch of desktops that are the same OS, same patch level, and be able to take advantage of it. That salt value per VM can be any string, and it will share between VMs that have the same salt value. So you can even set it up so that only certain VMs can share memory. Maybe they're less secure VMs and maybe a higher security virtual machine. You could, set a different salt value on it and allow it and keep it from being shared.
So you're saying we could have groups of VMs that share, group 1, group 2, group 3, or something like that, and those three will share between them. Okay.
Exactly. In fact, VMware View, they've actually put it into the user interface of the View environment in order to manipulate it a little bit. Unfortunately, it's only in the advanced settings within our regular GUIs here, within our vSphere clients. So this guy's doing a little better. His shared is, that's 30 gig. This guy's saving 27 gig due to transparent page sharing. 27, 28 gig. So it's doing even better. And this guy has, 192 gig in it, I think. So a little bit smaller host. These are dual hexacores, while this guy up here is a quad 10-core box. So, but very easy saving. Again, there's no balloon, probably no swap. No. So we're a very healthy environment here. Shouldn't be any compressed. I didn't turn on the compressed on this one. I guess I could easily enough and prove that to you. It's generally down near the bottom, although not always. Unfortunately, the headers here will not, there it is, will not actually sort in that screen. So again, very healthy environment. But here with these guys with no tools, it is coming in and doing much more aggressive paging without all the tools. Of course, in our production environment, we've got tools installed on everything, and it's all working great. So how's our share? Look at that, active 12. We're actually being able to take advantage of some of the swapping and sharing here going on. And what's the swap used? Update 7.6. Actually come down a little bit. As I say, it's varying, going through different pages and so forth. So there's an example. I'll let you go back to Sean.
All right, thank you, Dave. Let me make myself presenter and show my screen. All right, so we looked at some of the common counters, and Dave, were you going to jump into esxtop at all later on? I didn't see if you did that or not.
No, I didn't, but you got basically the same counters in there. I could, if you want, we can.
Yeah, we'll see how time looks towards the end. And we've been through esxtop before for some other things. The counters are pretty much the same thing with this as they are in some of the other CPU disk memory. So obviously these are unique to just memory, but esxtop works the same way. We'll probably towards the end have Dave jump in there real quick. And here's some other counters that are kind of important. Your V kernel memory, which is in megabytes, your page sharing here, your memory state. So these are just some of the more common
counters. Most of these counters are total for the host at the top of the esxtop screen.
Yep. Actually, not going to get into that. And here's just another tool we mentioned before. Visual esxtop is something you could use. So, Dave, why don't you jump into esxtop for a minute or two and just kind of show some of the memory stuff that you'll look at. So I'll make you presenter again and
sure.
Demo some of that.
We can do that. Didn't really think to do that as we went through a moment ago, but I actually do have a putty session open here. And here's those 4 VMs that I was looking at. The workload, they're 3 gig each, as you can see. A couple of them not granted a lot at the moment. Here's our swap current, so we can see per VM what the swap is. Swap target, it's actually swapping out a little bit more on those guys. This one's coming down a little bit. Reads per second, writes per second, so we can see the activity as it's actually going in and out. Let's see, let's go to fields, and we can look at mem control and see what's going on there with a J. And that's our balloon driver counters. So here's mem control size, no balloon. Of course, there's no target because there's no balloon driver. And we also see a max number on that one. Is mem control available or not? No, it's not there in. Okay, this is it enabled? Is it available? Tools aren't even there, so it's no. So that didn't do us much good. NUMA stats has some odds and ends in it, which since these VMs only have one proc, we're not giving them any NUMA information. NUMA information is given to VMs that have over 8 processors in them, 8 CPUs, and then VMware will tell it, okay, where the processors are, how much memory's on each group of processors. As it splits it up perhaps across multiple physical NUMA nodes, the VM will be given that information. There is actually variables in there so that you can control that and say, well, VMs over 4 processors, for instance, might be given NUMA information. If you're dealing with quad-core physical boxes, for instance, you might want to give it, any VM over 4 give that information to the host, to the virtual machine, so that it knows when it's split between NUMA nodes. VMware will always try to keep a VM within one NUMA node. As it moves VMs around with DRS, or even in the same machine, it will first move a virtual CPU to another core on the same socket. Then if it has to, it'll move it to a core on another socket, and of course DRS will move it to another host as a last resort to balance load. So it will move those around as necessary, trying to stay within the NUMA nodes. You also have a latency sensitivity setting within the web client that you can set, and if you set that guy on high, it will actually lock a VM to a specific core, and it complains if you don't reserve all of its memory. When you reserve a VM's memory, set the reserve on it, that memory is locked to the VM. It cannot be paged. It cannot be swapped. It won't even be compressed if you reserve the memory on it. So if you reserve CPU, megahertz, that's not quite as absolute, because a VM will voluntarily give up its memory when it goes into its wait cycles, but it goes to the top of the queue if an interrupt occurs and gets reloaded rapidly. If you have the high sensitivity set, that latency sensitivity set to high, it actually sets it up and sets kind of an overhead process there so that it doesn't even get swapped out of the CPU either, so that it will not give up the processor, and that processor is locked in as well. And you'll see a special counter in there for that. I've been playing with that a little bit here on one of my VMs. So let's see, what else can we look at here? NUMA, size, memory overhead. Oh, let me see. Is that what I think it is? No. All right, so leader world, mem allocations, pneumostats, active, mem active. Let's hit I. Look at mem active, get a little bit. Notice we've got percent active, active for, basically it's the same across on all of them. This guy's churning. These latest two that I just turned on are in a different place in their scan and their memory test, and they're 100% active at the moment. Let me see. Let me pop up just one other little demo here. We haven't shown this. Where is it? Oh, there it is. This is Visual Top, or a Windows, or there's actually a Linux version of this. And I'm going to connect up to a different server here. And this is Visual esxtop. Connect. Oh, hello. Let's try going to a host, shall we? Can't do it to vCenter. You have to do it to host. Duh. All right, so note here we get similar types of things. And got to kind of play with the headers here. Let's make it all wider so we can see things. But this is a little more flexible because you can actually right-click in the header and pick individual fields that you want to see. So there's CPU. We're talking about memory today. So if we want to look at any particular counter, we can actually pick it one at a time here in this this one. So here's our swap current, reads and writes. Unzip is our compression. Unzip per seconds, zip per seconds is our in and out. And so, come on, close out. It's a little picky. I can see it churning. It's actually got a script that's running here in a text window that's running behind this guy. And it doesn't seem, as you can see here, it's not real stable. This is a fling, so these are unsupported packages from our friends at VMware. Probably works better in Linux than what it does in here, because it's certainly not cooperating. We'll kill it and bring it back. So I'm it is back. I haven't had a lot of luck with the charts. You've got to let the thing settle in and get all of its data. But you can do a column filter equal to a certain value. Here's our disk partitions, disk path. So you get similar main screens, interrupt, power that we talked about earlier in the week. I'm running 100% CPU power. This particular host isn't real busy, so I've got quite a bit of halt state. And it's locked up again on me. Okay. Thank you very much for a really well-working program from the Fling people at VMware Labs. That's why it's not supported. Okay. So best just to come into PuTTY and do it there, or come into the clients and see it here. So here's our host. And again, it's going up and down a little bit as we've been running. I can do a refresh and see it for the entire hour.
All right, Dave, thanks. I'll go ahead and take this back over.
Yeah, go for it.
Oops. Let me see. All right, so I wanted to show you guys that visual esxtop because we talked about it all week long. So I wanted you guys to actually see what it looked like. Obviously, it had a few issues for whatever reason, but kind of cool. So as we mentioned, today was part 4 of our 5-part series. And December 29th, after Christmas, we'll be doing part 5. So as we mentioned before, we do have a class around all this. For those of you who are interested in getting some more advanced stuff, we do have that available. And then we've got our gift card giveaway for those of you that show up to all of these. So before I let anyone go, I'm going to stop the recording. If you have any questions, please ask those questions. We'll be more than happy to answer those for you.